Okay. So they say let the stochastic process n of t here be a Poisson process with lambda equals to 8. They say find the probability that this one means that the number of events occurring from the time 0 to the time 2.5 is 17. The number of events occurring from the time 0 to the time 3.7 is 22. And the number of events occurring from the time 0 to the time 4.3 is what?
It's 36.
It's 36. So he said you should find this probability. Okay. And but
Okay.
you see that this time frame 0 to 2.5, 0 to 3.5. 0 to 3.5 also includes 0 to 2.5.
2.5, yes.
So these time intervals are not independent. They are not independent. So we are going to break this time interval into mutually exclusive how do you call it? time. So that is, first we start from 0 to 2.5, then we'll start from 2.5 to 3.7. How many events occur between the time 2.5 to 3.7? Will be 22 minus 17.
Minus 17.
How many?
5.
5 events. So
yes.
Can you see the screen here? So between the time frame 0 to 2.5, 17 events occur. But between the time frame from 2.5 to 3.7, we have 22 minus 17 events. Because the time frame you are creating your probability should be mutually exclusive. You should not intersect. So we want to create times that do not intersect. So now the time frame from 3.7 to 4.3, number of events that occur between the time 3.7 to 4.3 with 36 minus 22, which will be 14.
14.
Are you seeing it? So
yes.
This set also can be written as this. That's 0 to 2.5, 17. Then 3.7, 2.5 to 3.7, 5 events occur. Then 3.7 to 4.3, 14 events occur. So we want to find these probabilities. So by independence, because the time frame now are now mutually exclusive, it means, what it means is that this and that are independent because they don't intersect. The time frame doesn't intersect. Have you seen it? So we say they are independent. If you don't do it that way, you can never solve the probability because you have to use the independent rule to break the three sessions into 3 mutually exclusive probabilities. So this and that are independent, and by stationarity, they have the Poisson distribution, which mean the first part, what's the time frame? What the time interval here?
Time interval is 2.5.
2.5. So the time interval here is 2.5. You know, we say lambda t. So you multiply the t by the lambda. The t is 2.5. The lambda is 8. So for the first part, this distribution, it will have lambda to be equal to 20. For the second part, the time interval will be 3.7 minus 2.5. That's the time interval. So you multiply that time interval by 8, that will give 9.6. So for the second Poisson distribution, it will have a rate, a lambda equal to 9.6. And for the last one, the time interval will be what? 4.3 minus 3.7. So you multiply that time interval by 8, that gives you the constant for the Poisson distribution. So this one has the Poisson distribution. That's the first one has Poisson distribution with parameter 20. This one has a Poisson distribution with parameter 9.6. And the last part has the Poisson distribution with parameter what? 4.8. So it means that probability, the required probability, will be equal to, you know, the Poisson distribution,
Yes.
raised to the power lambda.
Mm.
You remember?
Yes, please.
The power lambda, then lambda raised to the power lambda raised to the power n over n factorial. Here n is equal to 17. Remember?
Mm-hmm.
The first one n is equal to 17. The second one n is equal to 5. And the third one n is equal to 14. Have you seen
Okay.
it? Good.
Yes, please.
So this n is equal to 20. N is equal to 17 for the first one. N is equal to 5 for the second one. The n is equal to 14. Then lambda for the first one is 20. That's why this place is 20. And lambda for the second one is 9.6. And lambda for the last one is 4.8. So you put into the distribution, you simplify, and that will be the required probability. So the required probability, you say, I have not simplified, so you can simplify it later. It's the note I sent to you earlier this morning. So that's the answer for that probability. Let's look at another one. Another question. Please, have you seen the next page? Can you see page 6?
So is it question 2?
Question 2, yeah. So we are going
Yes,
to look at that question. It says defect occur along a cable according to a Poisson process, the rate of lambda equals to 0.2 per kilometer. So here the rate is what? 0.2 defects per every kilometer. So that's the rate. So if the number of kilometers were 2 kilometers, that it will not be the rate is always per unit, per unit time. So defect occur along the cable according to Poisson process of rate lambda is equal to 0.2 per kilometer. A is to find the probability that no defect, the probability of no defect in the first 2 kilometers. Have you seen it? Then the B said that given that there is no defect in the first 2 kilometers, what is the conditional probability of no defect between kilometer point 2 and 3? So we look at this. So first of all, what is lambda for this question? The first thing you need to note, determine is lambda, and it is given.
Lambda. Lambda is 0.2.
And lambda always, in this Poisson process, lambda always represent the occurrence, the rate of occurrence per unit time. Or this one per unit kilometer. This one is per unit kilo. For every 1 kilometer, we expect that 0.2 defects occur in every 1 kilometer. So it means for every 2 kilometers, how many defects do you expect to occur? It will be 0.4.
0.4.
For every 1 kilometer, we expect 0.2 defects. So it means for every 2 kilometers, we expect 0.4. And for every 10 kilometers, how many defects do you expect?
That is 0.2 times 10.
That will be 2.
That will be 2. That will be 2. Yes,
so it means when you have a 2 kilometer stretch of cable, we expect 2 defects to occur averagely. So the lambda here always gives us the unit, how do you call it? The rate per unit time. The rate per unit time. Good. So what is the A say? Let's start answering the question. So first we say let n of t denote the number of defects that occur up to what? 1 kilometer. Up to 1 kilometer t. The t is small here. I didn't make it big. So later you can make it. So 1 kilometer t. Have you seen it? So end of t denote the number of defects that occur up to 1 kilometer t. Good. So for the first one, I say we should find what? Find the probability that no defect in the first 2 kilometers. So it means in the first 2 kilometers from 0 to 2, the number of defect is 0. So this is the probability. So you should be able to, this one, you should be able to translate the words there into statistic notations. Have you seen it? So what they want us to determine here that there'll be no defects.
No defect.
The probability that no defect occur from the distance 0 to 2 kilometers. You should find the probability that no defect occur after 2 kilometers. Have you seen it? That or from 0 to 2 kilometers, there will be no defect. For a distance of 2 kilometers, there will be no defect in the cable. That's what the question says we should determine. So we wish to find this. But n of 2 has a Poisson distribution with parameter 0.2 times 2, which is 0.4. Because we know that in every kilometer, there is 0.2 defect. So in 2 kilometer stretch, we expect to have what? 0.4 defect averagely. Have you seen this? So what's the lambda?
Now our lambda will be 0.4.
That's the rate now with 0.4. So in the Poisson distribution, you replace the lambda t by 0.4. And how many defects? What's the number of defects? 0. So it will be raised to the power 0. Then e raised to the power minus 0.4 over 0 factorial. So that's the answer for the A. So simple. So it will be e raised to the power minus 0.4. Are we okay? Great. Then the B part says, given that there's no defect in the first 2 kilometers, given that there's no defect in the first 2 kilometers, see the way I'm interpreting the question. Given that there's no defect in the first 2 kilometers, it says, what is the conditional probability of no defect between the kilometer point 2 and 3? So between the kilometer point 2 and 3. So between the distance of 2 and 3 kilometers, between those two, what's the probability that no defect will be recorded? So this is what we wish to determine. The probability that between 2 and 3, there'll be no defect, given that between 0 and 2, there's no defect. So since the events which occur in the disjoint time interval are independent, it shows that this time interval 2 to 3 and the time interval 0 to 2 are independent. The time does not intersect. There's no overlapping in the time. That's the time from 0 to 2 and the time from, not the time, the distance from 0 to 2 and the distance from 2 to 3. They don't overlap. It means the two random variables, that's n3 minus n2 and n2 are independent. And because they are independent, we can write this probability. It means this condition will not be relevant when they are independent. It will not affect the probability. So you can remove the condition because of independence. So the probability is the same as the probability that no event occur between the time interval 2 to 3. And between the time interval 2 to 3, it's only 1 hour. It's only one unit. Please, you get it? Between
yes,
2
please.
to 3 is 1 unit. And 1 unit, the rate is what? 0.2. So you see here, I use a 0.2. I didn't use 0.4.
Okay, 0.2.
Because the time interval here is only 1 unit.
It's only 1 unit. Okay.
In the A, the time interval is 2 units. But here, the time interval is only 1 unit. So we use the time interval, the rate for 1 unit. That's 0.2. So that's why here we use 0.2 to solve which gave us this answer. I hope it is very clear. So I'll move to the next slide. Are we okay?
Yes, please.
Great. So question 3. All these questions are in your notes, and I'll provide some more questions also under that you can try your answer. They are all past questions, and some of them are in the book, in the stochastic process book. They have been solved. Some of them have been solved in the book. So a customers arrive in a certain shop according to Poisson process of rate lambda is equal to 4 per what?
Per hour.
Per hour. So it means we expect that in that shop, every 4 hours, they receive 4 customers. Every 4 hours. It is expected. It's an average. You know, it's an expectation. It is expected that every 4 hours, they receive what? 4 customers. So how many customers do you expect in 2 hours?
That would be 8 hours. Eight customers.
8 customers. We expect that in 2 hours, 8 customers will arrive.
Yes.
And how many customers do you expect in 5 hours?
That would be 20.
20. That's 5 times 4. So
yes, please.
You always look at the number of hours, noting that the rate given here is per unit time.
Per unit. All right.
Always know that the rate given is per unit time. This one, the unit time is 1 hour. It's not minutes, it's not seconds. Sometimes it could be seconds, sometimes it could be days, sometimes it could be years. Have you seen it? But this one is talking about in hours. So the unit rate, the speed, the rate at which customers arrive in that shop is what? 4 per every hour. Joe, look at Joe. Okay, so we expect that. Okay, how many customers do you expect to arrive in 10 hours?
10 hours, it will be 40.
40.
Maybe 10 times 4.
10 times 4. Good. You get it now. You are doing well. You are doing excellently well. Okay, so given that the shop opens at 8 a.m., so time 0 will be 8 a.m. because the shop open at what?
Will be
8 a.m. So 8 a.m. will be what? Time 0. So at 8 a.m., at 8 a.m., how many customers will be in the shop?
That'll be 4.
It will not be 4 because at 8 a.m. they have just opened. So there will be no customer. The shop is supposed to open at 8 a.m. So at 8 a.m., there will be no customer in the shop.
Okay.
So at time 0, we assume that that's one of the assumptions for the Poisson process. We assume that at time 0, there's no customer.
No customer.
Have you seen it? At time 0,
yes.
There's no customer. Have you seen it? So he said, what's the probability exactly one customer has arrived at 8:30? 8 to 8:30, how many hours?
That'll be 30 minutes.
We are dealing in hours, not in minutes. Otherwise, you confuse yourself.
In hours.
Good, because the rate is given per hour. So we calculate everything in hours.
So, all right.
So from 8 to 8:30 is how many hours?
A half hour.
Yes. So that's 1/2.
1/2, yes, please.
Have you seen it? So
yes.
Look at the question again. It says, what is the probability that exactly one customer has arrived by what?
By 8:30
a.m. And the total of 5 customers have arrived by what? 10:30 a.m. From 8 a.m. to 10:30 a.m. is how many hours?
It will be 2 hours, 30 minutes.
That's 2.5 hours.
Yes, 2.5 hours.
Good. And from 8 a.m. to 8:30 is how many hours? Half an hour. So that's why we wrote the time here, half an hour. Have you seen the solution? When we're solving, here is half an hour. And the second time is 2.5 hours. That's 5/2.
Okay.
Have you seen it? So this is the probability you want to determine, that within the first half hour, only one person arrived. We want to find the probability, and that after 2.5 hours, 5 customers arrived. Please, have you seen it?
Yes, please.
Great. So, but from 0 to 0.5, and also from 0 to 5 and 2.5, that time interval is not mutually exclusive. So we have to create a time interval which is mutually exclusive so that we use the rules of independence to solve the question. So first of all, we divide the time into 2. First of all, from the time 5, 2.5 to 0.5, that's this interval. Have you seen it? And also the time from 0 to 1.5 also form one interval. So these two time intervals are mutually exclusive. The number of events that occur between two time intervals that are not overlapping are mutually exclusive. So we can use the rules of independence. So this probability is the same as the probability that only one event occurs from 0 to 1.5. And from 1.5 to 2.5, how many events occur? It will be 5 minus 1.
Yes, so 4 events.
4 events. Because as at this, only one event. As at here, 5 events. So in between the two time frame, it will be 4 events. That from 0.5 to 2.5, we have 4 events. And because of independence, we can break them into two probabilities like this, multiplying each other. So find the probability that this is equal to 1, and n is equal to 1, and we'll find the probability that n is equal to 4. Have you seen it?
Yes.
Between 1.5 and 5, between 0.5 and 2.5 is 2 when you find the difference. So that's why this place is 2. So here, what is the time here? The time here, interval here is 2, and the time interval here is what? Half an hour.
An hour.
Have you seen it?
Yes,
so
please.
The rate for 1/2. If 4 events happens in 1 hour, how many events will happen in half an hour? It will be 2 times 4, which will be 2.
2, yes, please.
Have you seen it? So here, the lambda will be equal to 2. And here, what will be the duration here? Is 2 hours. 2 hours, how many events are likely to take place? It will be lambda times 4, which will be,
so it will be 8.
Which will be 8. Have you seen it? So that's why this place is 4 times 2, which is 8. And this place is 4 times half, which is what? 2.
Okay.
Have you seen it? So here we use 2 as our rate, as our lambda, and here we use 8 as our lambda. Then you simplify. You put into the Poisson distribution, and then you simplify, and that gives you this answer. Are you okay? So we move to the next question. By the time we get to the 5th question, we'll be okay, because it's the same thing, but using different examples to illustrate the same thing to you. So let's go to question 4. Have you seen question 4?
Yes, please.
I'll soon finish. The last question is question 5. The last question is solved, so we'll soon finish. So the video will not be too big, so I can send it to you. So question 4. Suppose that earthquakes occur in a certain region in accordance with a Poisson process at the rate of what? 2 per week. So here was the rate. 2 earthquakes averagely occur per week. That is too much. If you are in an area where every week 2 earthquake occurs, it's too much. Even if in a year, cry is too much. Because in Ghana, I don't know the last time earthquake took place. Sometimes it takes 10 years before 1 or 2 may occur. But 2 per week here is at a high rate. Have you seen it? But in that time, 2 earthquakes occur averagely, in the average, every week. So in 4 weeks, how many earthquakes do you expect to occur?
2 times 2, which is 4.
In 4 weeks, how many earthquakes do you expect to occur?
So in 4 weeks, we expect 4 earthquakes to occur.
No, 2 earthquakes occur in every week. So in 4 weeks, how many earthquakes do you expect?
8.
8.
Yes.
These things
Yes,
are very important because when you know the rate, then you can always determine your lambda you are going to use for the Poisson distribution. Have you seen it? So
Yes.
the first question A, find the probability at least 3 earthquakes occur during the next 2 weeks.
Yes.
At least 3 earthquakes. At least 3 means 3 or more. Is that not so?
Yes.
So first we define NT to denote the number of earthquakes that occur up to the week T. The number of earthquakes that occur up to the week T. So N2, what do we T here? N2 here, it means T is equal to 2. Have you seen it?
Yes.
T is equal to 2. So the number of earthquakes in 2 weeks will be 2 times 2 because the rate is also 2. So it will be 2 times 2, which will be 4. So here we are going to use lambda to be equal to what? 4.
4.
Have you seen it? So the question said that we should find the probability that the number of earthquakes in 2 weeks will be greater or equal to what? 3. At least 3 means 3 or more. Have you seen it?
Yes, please.
3 or more earthquake occur after 2 weeks. So it's the same as 1 minus no earthquake after 2 weeks. At 2 weeks. Have you seen it? If 3 or more earthquake occur after 2 weeks, it's equivalent to saying that, okay, it means within the first 2 weeks, either there was no earthquake or there was only 1 earthquake. No, so there are 3 options. If 3 or more earthquake occur after 2 weeks, it means within the first 2 weeks, either there was no earthquake or 1 earthquake or 2 earthquakes. Please, do you understand? They say after 2 weeks, what's the probability after 2 weeks? 3
Earthquakes will occur.
3 or more earthquake will occur. Have you seen it? So if after 2 weeks we expect 3 or more earthquakes, it means with the first 2 weeks, either there was no earthquake or there was only 1 earthquake or 2.
Or 2. Yes, 2 earthquakes.
Or 2. So the probability of at least 3 earthquakes will be 1 minus, probability. When they say 3 or more, the opposite will be either 0, 1, or 2. The opposite.
1 or 2. Yes.
Have you seen it? So we are using the converse, the opposite, to solve it. So it will be 1 minus this. But we know the rate to be equal to 4. So first you put lambda to be equal to 4 and a is equal to 0. They say it's left with 10 minutes. Lambda equal to 4, n is equal to 1. Lambda is equal to 4, n is equal to 2. You put it to the Poisson distance to get this equation. You simplify it, you'll get this answer. Please, are you okay?
Yes, please.
Great. So we'll look at the B part maybe 2 days from today. the continuation. This is not the end. This is the first part of
Mm.
it. But there's a question here, question 5, which has also been solved. So you go through, it has been solved. It's just similar to the one I solved, the question 1 I solved. This is also a past question. Then the remaining questions have not been solved. They are question 6, 7, and 8. So if you understand question 5, which has been solved, question 1 to 5 has been solved.
Mm.
In all these questions, first of all, know the rate. Here, question 5, what's the rate?
Question 5. Yeah, the rate is
It's
3.
Have you seen it? It's 3.
Yes.
So once you know the rate and you determine the time, first of all, here the time is what? The time is 1. What is inside the bracket here is 1. Here the time.
This one.
So at time 1, what's the probability that 2 events will occur? At time 2.4, what's the probability that 6 events will occur? At time 4, what's the probability that 11 events will occur? So what will be this probability? So that's what we want to define. First of all, this one means time from 0 to 1. This one means the time from where? 0 to 2.4.
From 0 to 2.4.
This one means time from 0 to 4. But these times are not mutually exclusive. They intersect.
Yeah,
0 to
yes.
1 is inside 0 to 2.4. And 0 to 2.4 is also inside 0 to 4. So we want to create a mutually exclusive time. So what we do is that first 0 to 2 will stand alone.
Stand alone.
Have you seen it? Then
Yes.
we'll do this minus this. That
Minus this.
2.4 minus 1.
1.
And 2.4 minus n1. How many events? Will be 6 minus 2,
Will be
4.
yeah.
Then this minus this will give you 5 events. So once you do that, then you get mutually exclusive sets. Then when you find the probability, you can add them. So here, how many events? Here, how many events? 2 events. Here, 4 events and 5 events.
5
What's
events.
the time here? What's the time interval here? 1.
1.
And then the time interval here will be 2.4 minus 1.
Minus 1.
No, the time interval here will be 2.4 minus 1. The time interval here will be 4 minus 2.4. So here, what's the time interval?
It's 1.
1. Here, what's
Yes.
the time interval?
That will be 1.4.
1.4. That's 2.4 minus 1. And here, what will be the time interval?
That will also be 4 minus 2.4, which is 1.6.
Good. So the time here is 1. The time here is 1.4, and the time here is 1.6. So you multiply this 1 by lambda to get the rate for the first one. Are you getting me?
Okay.
Then you multiply the time here, which is 1.4 by lambda, which will be the rate here, which is 4.2. Have you seen it? Then you multiply the last time interval by lambda, which will give us 4.8. So the rate here is 4.8, the rate here is 4.2, and the rate here is 3. 3 is the normal rate which was given. But because the first one is only 1, it's 3.
1. Yeah.
Have you seen it?
Yes, please.
So that is that. So you use that thing to solve the question. So the same thing applies to the B part. It's also a conditional probability. So this one, whenever you are giving the probability, you just have to find times that are mutually exclusive and use it to solve the probability. Have you seen it? Good. You have to find times that are mutually exclusive. So you can use the same principle to solve question 6, 7, and 8. So the above questions are all solved and they are in your handout.
Okay.
We use it to solve questions number 6, 7, and 8. So that is that. We'll continue most likely on Thursday.
Okay.
Good.
All right. Thank you
There's no
much.
question. I hope there's no question.
So we'll go through. For me, I'll go through, and if there are some hitches.
Okay. So God richly and abundantly bless you. Is what's the name of the lady?
Grace.
Is she still on it? Or she's gone?
Okay, I think she's gone.